Okay, so this is what I stopped at last time. I had described how images can be viewed as graphs, and
Excuse me,
we
ma'am.
were just going to start the discussion on graph cuts. So graph cut, I had described
Hello,
that
ma'am.
it's yes. Hello.
Ma'am, could you rotate this, please?
Repeat this images as graph.
No, could you rotate the screen?
Oh yeah, sorry. Yes, thank you, thank you. Yes, yeah. So images can be viewed as graph by thinking of the pixels as nodes or vertices, and by assigning by assigning an edge to every pair of vertices, and weights can be assigned to every edge depending on the feature that you're interested in. So here, this weight that has been given here is based on the intensity, but this is not the only weight that you can assign. There could be other possibilities for weights also. So in this way, an image can be viewed as a graph, and the algorithm for graph cuts in which is an algorithm in generally in computer science or in spectral graph theory, can be applied for segmentation. So I will describe the method briefly. I will not describe the algorithm because it will take quite a while to go into the details of the algorithm, and also it is a very like there are many implementations of it, so it's not new or anything. It's been there for a long time. But mainly, if I have to describe it, there's a lot of detail to be described. So, but I will tell you what is the idea behind graph cuts. Okay, so the graph cut algorithm is based on this max flow min cut algorithm in graph theory or network flows, where one wants to see what is the minimum cut or minimum or a partition such that the sum of the weights between edges that go from one part to the other or one subset to the other are minimized. Okay, so that weight has to be minimized. It has been shown that this minimum cut also maximizes the flow from the source, which is assumed to be in one set, to the sink, which is assumed to be in the other set of the partition. So this is our notation. V and E are the set of vertices and edges of the graph G respectively, and A and subsets A and B give a partition of the edge of the vertex set V if these two conditions are satisfied. The union should be the entire set and the intersection should be empty. So when we mean a partition of a graph, we mean subsets A and B of the vertex set that satisfy these two conditions. And we define the cut between AB. So this is going, so we want to minimize this, right? Minimize this sum of edges. So we will define what that sum of edges is first. So it is the sum of the weights, some WUV, where U is in A and V is in B. So you have, suppose you have some graph, a set of vertices, which you have partitioned into two sets, and then you have edges between all of these, right? So I'm just drawing a few, but you have more, and there are weights to all these edges. So here is your A and this is B, and you're looking at the sum of weights of edges which join a vertex U in A with a vertex V in B. So look at all such pairs and take the sum of their weights. That is defined as the cut between A and B. Okay. This is the quantity that we seek to minimize. Okay. And the max flow min cut theorem, uh, actually these are two problems. The max flow is one problem and min cut is another problem, and as a result it says that solving one problem solves the other also. Okay. So I'm just describing briefly what these two problems are. These are dual problems in combinatorial optimization. So the notation is as before. Okay. And the only assumption is that there's a designated vertex called a source and a designated vertex called a sink in both the places, okay, yeah, for both the problems. So if we look at the min cut problem, this is what I had described earlier, that this is the quantity that you want to minimize. So you want to find a cut. In this case, I'm calling it S and T instead of A and B. You want to find a cut S tilde, T tilde, so that the total weight with respect to that cut is minimum. That means W S tilde, or this is actually what earlier we called cut. Okay, that's the same thing here. So W S tilde T tilde should be less than WST for any other cut. That is what is the problem of minimizing cut. On the other hand, the max flow problem says that, so first of all, a flow from a source to a sink is a function f that satisfies certain properties. So one of the properties that it satisfies is that the if you look at the flow at any edge E, then that is less than the maximum allowed flow at that E. So it just that it doesn't exceed the capacity of that edge. And a conservation of flow, which means the total flow into a vertex is equal to the total flow out of a vertex. Okay. So with these, any function that satisfies these two conditions is called a flow. And for such a flow, the value of the flow at any vertex, the value of the flow is the net flow out of the source S. So you have a source and you have all these various vertices that might be joined to the source. Then the value of the flow is given as the sum of all those flows out of the vertex S, okay, where S is the source. Now, using the conservation of flow, it can be shown that the total flow out of the source is equal to the total flow into the sink. So this Vf can also be written as the sum of all Fe such that E, all the edges that are incident into T. Anyway, so this is some general theory. And then the problem of maximizing flow is to find a flow such that V of F is maximum, which means you find an assignment of this function F to the edges so that this flow becomes maximum. And the key lemma that connects this V of F with this W, the cut and the flow, is that if F is any flow and ST is any cut in a directed weighted graph G, then the value of the flow, so value of the flow for any flow is always bounded above by the cut given by S and T. Okay, so you have any partition, then the value of the flow coming from that partition is going to be bounded above by the cut given by the partition. So essentially, this is saying that if you determine this, then you have determined the maximum flow that can occur, right? Because the maximum flow is less equal this. So if you've determined a minimum for this, then that is a maximum for this, and vice versa. If you have determined a maximum for Vf, then a cut that satisfies that is going to be the minimum cut. Okay? So essentially, this is the lemma that says that one problem is equivalent to the other. So moving on. So this max flow min cut theorem, if you want to find such a partition, there is a naive way of doing it, which is you just simply find all the partitions of the graph. Okay, and for each partition, you find out the weight or the cut and see which one is minimum. But that naive idea is too expensive because you have too many. So the number of partitions will be 2 raised to n. Okay, and so this is a polynomial. Even though it is computationally prohibitive, there are polynomial time algorithms. But of course, one does not want to go this way. There's no reason to try and find all of these partitions. So yeah, so how does an image segmentation problem get solved by a graph cut solution? Is simply by thinking of segmentation as a flow problem, and you select weights so that the minimum cut gives you some kind of meaningful segmentation. Okay, so essentially what is being done is that you use the graph cut algorithm to partition the pixels. Okay, and then the pixels in one set form one part of the segmentation, okay, or one region, and pixels in the other set form another region, okay. Now, uh, suppose you threshold this and you realize that this does not really give you what you want, okay, then you have to uh, sort of redo it, retune it by choosing a source and sink. So this choice of source and sink is, so for example, in MATLAB, if you use the graph cut algorithm, it will let you choose a source and sink. So suppose you know what you want in the foreground and what you want in the background of your segmentation, then you can choose a source and sink accordingly and then do a graph cut. So essentially, that is how a graph cut will lead to a segmentation. Okay. Um, yeah. So this basic graph cut algorithm turns out that it leads to some sets of isolated nodes in the graph. So there's some problem that appears, and this is very common, which is that usually it will give you a partition of this kind, where you have some kind of isolated node and the rest of the graph or the rest of the vertices in another set. Okay. So this, I mean, there are papers that have dealt with this problem. And so the normalized cut algorithm was proposed in 2000. So normalized cut takes care of this problem by making sure that, so instead of just minimizing this cut, instead of minimizing, sorry, instead of minimizing this quantity, it minimizes a normalized quantity. So yeah, so one defines the normalized cut by, so what is the difference between that cut AB and this cut AB? So here we are looking at cut AB divided by associations between A and B. What this means is you're looking at, again, you're looking at W, U, Z, but now U is in A and Z, once you have fixed U, then Z is all the remaining vertices. Okay, not just in B, but in those vertices maybe in A also. Okay, so you are normalizing this quantity. So here you are looking at just connections between A and B, but here you are looking at connections between every vertex of A and the rest of the graph. Okay, and summing over all those connections. So this normalizes this cut. So you do this with respect to A and you do this also with respect to B. Okay, so this in some sense normalizes the cut, and essentially it avoids that problem of separating out isolated points by making sure that the partitions with isolated nodes don't have a small value. Okay, so with this normalization, what will happen is that because cut AB and association AB will have the same value when A is a single node. If you have a partition like this where A is just one node and B is the rest of the graph or the rest of the vertices, then in that case, when we do this, when we look at this quantity, cut AB over associated AB, then this is going to be 1. Okay, so it will be 1 plus something, so that this normalized quantity will be greater equal 1. Okay, and so it will no longer be the minimum, and so this kind of partition will never be given as the minimum cut partition. So essentially that is what this method does, and it improves the graph cut. Yeah, so finding normalized cut is an NP complete problem, but it can be viewed as a generalized eigenvalue problem. Okay, and then that generalized eigenvalue problem can be solved. Uh, in fact, can be still further reduced to a simple eigenvalue problem, and then that can be solved using standard eigenvalue methods. Okay. Um, yeah, so this was just a comment about the weights that I was making earlier, that the weights need not take only intensity, but also distance. There can be different possibilities for defining the weights. This is the main point. What are graph cuts suitable for? So what graph cuts will not do is, for example, in an image like this, it will not segment out, say, windows and building and sky and roof. So not the various parts in that way, but it will give you a rough segmentation into the main regions of the image. So here it was only building and sky. Okay, so it will give you a very rough segmentation, and it can be sort of the beginning, or when you require these broad segmentations, not really detailed segmentation. Okay, so not if you want to maybe if you want to segment an image containing blood cells or something, maybe that is not a suitable place. But if you have scenes where you want to just segment out the main things that are seen in the image, okay, so maybe cars on a road, okay, so there are just sort of two things there. There is cars and there is the road, okay, so just two principal objects. uh, then graph cuts is suitable, okay. And so for example, in autonomous navigation, or if you want to search image databases for something and you want a quick segregation of images, then graph cuts are useful, okay. But if you want finer level segmentation, then one does not go for graph cuts. Yeah, so as I said, I'm not going to into the details of this Shih-Malik algorithm, but it is I think some of the DA students have already presented it in the first year, but I also think that some DA students are presenting it this year also. Okay, so there might be a group who's studying the Shih-Malik algorithm or spectral graph theory. That is definitely one group. And if you're interested in listening, I can tell you when they are presented. Okay, so it's very interesting how this graph cuts leads to an eigenvalue problem, and the eigenvalue methods that you might have seen earlier are applicable here. All right. So then that's about graph cuts. That's the main idea in graph cuts. Yeah, so another thing I must remark is that nowadays when you use graph cuts, it is mostly the normalized graph cuts that is used. Nobody uses the basic graph cut algorithm. Okay, segmentation using watersheds. Now, until now, whatever ideas we have seen, this one is entirely different from that. Okay, so this is more like a morphological idea. Uh, um, where the okay, I'll describe the algorithm. You will see in the end how morphology comes into play. Okay, so here in watersheds, what is done is you sort of um, imagine your image in 3D as so you have your pixels on the XY plane and intensities on the Z axis. Okay, so here is let me just show you a picture right away. So here is the image. Okay, and you view this as a topographical image, which means now you're viewing the pixels in the XY plane. Okay, so those are the, but these whiter regions will be sort of above the black region. Okay, so this is in 3D with the intensities playing the role of height. Okay, so the black region, for example, will be at the bottom of this topographical image, and the white, wherever there is bright white, that will be the top peaks of this topographical image. Okay, so the idea of watershed algorithm is first you view the image as a topography, and then you think of uh, flooding this topography with water. Okay, starting with the minima in the region. So you think of it as the minimum or the lowest points of this topography. Suppose you start filling water at those lowest points. Okay, and the water is rising along this topography. So rising along the intensity. Okay, at the same rate. Okay, then the region. So first of all, here in this image, you can see that this is going to be a region of minima, and this is going to be a region of minima. Okay, this is gray, so this is at a height above this one. Okay, so this is at the bottom and this is at the bottom. So if you start filling water along this region, okay, and you start filling water in this region of minima, then as the water slowly rises above here, okay, suppose it reaches this height, okay, then it's going to start flooding over, or pouring over into this other region, okay. So and then slowly it will rise even more, and it will start overflowing into, or maybe these two regions will merge, okay. So whenever the regions start merging, we try to build a dam over those, between those regions, okay. So for example, when the water rises up here, we build a dam here, okay, and so on. So the dams that are built in this way to avoid the water overflowing between the original regions of minima, those dams in the end give us the segmentation, okay. So just to describe this picture further, so this is the uh, base. So this is the starting point. So when the water starts filling in, okay, so here there is going to be water, okay, and here there will be water. So that's this image. So here there's water, here there's water, and now you can imagine it slowly rising, okay. So as it's rising, it will fill up this part, okay. At some point, it will rise to a level where this level is same as the original level here, okay. And then once these once the water rises to the level of this, then now this is also a point, this is also where you will start filling water, okay. So now you start filling water here also, and slowly the water starts rising in both places, and at some point it will overflow, okay. If this region, or if this ridge is lower than the rest of the ridges, then there will be overflow between these. When the overflow, when you reach the point that there will be overflow, you build a dam here, okay. Similarly, it looks like here at some point these two regions are going to merge, then we build a dam there. Here also there's a dam, okay. So finally what happens is, as the water will keep on rising, okay, flood the entire topography, you will have built all these dams, okay, to avoid water going from one region to the other. And this is the required segmentation, okay. So now finally this image, you would expect that it is broken up into regions, like this is one region, this is one region, this is one region, okay. These will also supposed to be, these will also give us some boundaries, right? So if that is the expectation, then that is sort of fulfilled by this segmentation, okay. So this will be the end of the watershed algorithm for this image, okay? So that's the general idea. And building of these dams is essentially done using morphological process, okay. So so suppose that these were the earlier two regions of minima, and after flooding these have started connecting, then uh, sorry, then one uses this morphological structuring element to, first, this part is eroded, okay, to separate out the regions, and then one builds this by doing some kind of dilation, okay. So dilation and erosion both are morphological processes, which I will describe in a morphology lecture, okay. But essentially what it does is, if you pass this structuring element or this mask over these pixels, then it's going to erode. Erode means remove or reduce the intensity values along these pixels, along this border, okay. So this darker gray becomes the lighter gray. The effect is that, so if you run this over all these boundary pixels and all these boundary pixels, the effect is that these two regions get separated, okay. And now you have separated out the water which was flooding and sort of overflowing. You have separated it out, you made the space, and then you build a dam there by using this idea called dilation, okay. So that is the idea of watersheds. Then we can look at a few details of it. So to make this idea precise, I describe the topographical formulation for you. We consider three kinds of points. Points which belong to a regional minima, which means local minima. So there will be, we will divide all the pixels into three classes. One, those are where you have a minima. So by the way, this minima is with respect to the gradient image. Okay. So the way in which watershed algorithm works is it first looks at the gradient image. In the gradient image, you look at the points which have minimum intensity. Okay. Okay. So there will be some points of minimum intensity. Then there are something called as uh, this catchment basin or watershed, where points, if you place a drop of water, the drop will certainly trickle down to one of the local minimum. So for example, in this image, this is a watershed region. Okay, because if you sort of put a drop of water here, it's going to go down to this minima, or this is also a watershed region. Okay, so simply the regions that slope toward the minimum, those are watershed region. Okay, so this is the watershed region for this minimum, and this here outside is the watershed region for the outer minimum. This is the watershed region for the minimum that will occur here later on. Okay, and so on. So in this way, the entire image can be divided into uh, these. And finally, there will be points at which the drop of water is equally likely to fall into one or more of the minima, which means the points on the ridges up here. Okay, so a point on the ridge up here is equally likely to fall either in this watershed area or in this watershed area. Okay, so in this way, we have divided all the pixels in this topographical image into three classes: points of minima, points of watershed, and points which are on the ridges. In the end, it is the points on the ridges that will form the watershed lines. Okay, those will be along the dams. We will see later. But the point is, it's not only those on the dam, only those that form the line. Okay, there will be others, and that is why this algorithm you have to do. Otherwise, you could just take the ridge points and call them your watershed line, right? So, but that does not happen because not all the ridge points are at the same level of intensity. Okay, so you cannot just take all of them and call that your segmentation. Okay, so the objective is to construct these watershed lines or these dams in the end. Okay. The idea to do this is by imagining a situation in which water is allowed to flood into the topographical region from holes at the local minima at a uniform rate. So the height of the mountains is proportional to intensities at those points, as I described earlier. As water is allowed to rise, it will flood a watershed region and overflow into another. So when it begins overflowing, that's when we build a dam between the two watershed regions. And in the end, it is going to be those dams, because we will do flooding till the end, till the highest intensity level. Okay. So it is in the end, the dams will provide the watershed line and finally give you a segmentation of the image. Okay. So the outline of the algorithm is as follows. So you take M1 up to MR, suppose, being the local minima of an image. Okay. So typically, as I said earlier, this image is going to be the gradient image. I hope you remember what the gradient image is. So if you have your original image given by fxy, okay, fxy is your original image, then you can compute the gradient image gxy. Uh, so you compute gx, gradient in the direction of x, gradient in the direction of y. Okay. And how do you compute this? You can compute this using any of the gradient operators. If you want to use 2 by 2, you can use the Roberts operator. If you want to use 3 by 3, you can use Privet or Sobel. Okay. So using any one of those operators, you can compute this gx and gy, and the gradient image is taken to be mx comma y. Well, typically you would expect it to be this, okay, but to reduce the computations, it can also be taken to be mod gx plus mod gy, okay. So gx and gy will be two images, gradients in the direction of x, gradients in the direction of y, and then you take the sum of the moduli of those elements and you form this image. This is the gradient image. Okay. So the starting point of the watershed algorithm is usually the gradient image of the given image. Then you look at the watershed. So you CMI is going to be called the watershed corresponding to the minimum MI. Okay. So for example, in this, these are the watershed regions, right? One, this is another, this is another. Okay. So these are all, and here is another. Okay. So these are all the watershed regions. Okay. So these are the characteristic is that they are all connected. Okay. The pixels in these regions are all connected to each other. Okay. So these are all connected watershed regions. Containing the minimum MI. Okay. And we will say T of n is the set of all pixels that lie below the plane gxy equal to n, which means set of all pixels that lie below a certain given intensity. Okay. T of n is set of pixels which have intensity less than n. Okay. If you are thinking of it as this topographical image, then it is going to be set of all points below a certain height. Okay, so T of 1 is set of all points below height 1. T of 2 is set of all points below height 2, and so on. Okay, so we have this notation. Now you start, the topography is flooded at integer increments from n equal to minimum plus 1 to n equal to maximum plus 1. Okay, so minimum, assuming minimum is 0. Okay, then you start filling at integer increments, which means the flooding will be from level 0 to level 1, then level 1 to level 2, and so on. Okay, so level by level the flooding is done, and then at each point one takes a view of what are the connected components, what are the are there any new components or watershed areas coming into the picture, and are there any watershed areas that are merging. Okay, so at every level of uh, incrementing this n, one will see what Cn is. So Cn is union of all the CNMI. CNMI is the watershed at the nth stage of flooding. Okay, all the watershed at the nth stage of flooding. So this CMI was C0MI. Okay, at the zeroth stage, you had just the the regions that I described earlier. And then at the first stage of flooding, which means when the water level rises from 0 to 1, there will be some number of connected watersheds. Those you take. So C1 will be C0MI plus C1M, or union C1MI, and so on. Okay. So at the stage N, you look at all the watersheds at that stage of flooding, essentially. Q is the set of connected components of Tn, which means suppose you are looking at just the uh, topographical image below level n. Okay, so below every level, see the number of connected components changes or can change as the level changes, right? So here, for example, if you were looking at level 0, okay, and if you wanted to look at the connected components, you would see 1, 2, 3, 4, 5 1, 2, 3, 4 connected components. Okay, but now if this level goes on rising, okay, sorry, no, not 5. You would see 3 in the beginning, just 1, 2, and 3, because these are the minima. Okay, so C0MI is just 3. This is not black, so this won't be there in the first part. Okay, so you will have only 3, but as the level rises above this gray level, above this gray intensity level, then this is one more connected component that's going to come into the picture. Okay, so as n rises, the number of connected components can change. So now depending on as this n rises, depending on each connected component in Q, you have three possibilities. One is that uh, for any connected component, that component intersections Cn minus 1. Cn minus 1 means all the watersheds that were there at the n minus 1 level. So this intersection Cn minus 1 is empty. This means that you have encountered a new minimum. Okay, this minimum was not included in the earlier watersheds. Okay, so this when a new minimum is encountered, in this case, what you do is you add Q to the list of watersheds. Okay, so you add Q to Cn minus 1 to form Cn. So this is if Q intersection Cn minus 1 is empty. The other possibility can be that Q intersection Cn minus 1 contains one connected component of Cn minus 1. So you have a new connected component which contains one of the already existing watersheds. In that case, you simply merge these two. Okay, so you just merge Q into CMI, which means you add it to Cn minus 1 to form Cn. Okay, so this adding is different from this. In this case, you are adding a new component. Here, you are just merging into it's merging into the connected component that lies in Q. Okay. And finally, Q intersection Cn minus 1 contains more than one connected component of Cn minus 1, which means now you have found a region. So when this flooding reaches a level like this, okay, so when the water level has risen to a height, so that these two regions are merging. Okay, so there is this region and there is this region, but now Q will be this whole thing. Okay, because it won't see this ridge. The water will have flooded above this ridge. Okay, so then for that Q, when it starts to flood, when this overflowing begins, okay, then you build a dam to avoid overflow of the catchment basins. Okay, so as soon as, so you see the flooding will not be sudden. Most often, these intensity levels will not be uniform. Okay, so if they are uniform, then you will not see Q in the earlier level, but you will see it in the next level suddenly. Okay, either way, okay, if you see that a new Q is being added, which contains two or more of the earlier watershed, then you know that at that point you have to stop and build a dam. Okay, so uh, this is how it proceeds. Okay, as the water level rises from level n to level n plus 1, you take a stock of what are the connected components. You see if this is a new connected component which was not there earlier, then you add it to your list. If you then if it's a connected component which was part of an earlier watershed or which contains an earlier watershed, you just merge it. Okay, and if it is a connected component which contains two or more earlier watersheds, okay, then you realize that flooding is occurring between the watershed, so you build a dam. Okay, so there are these three possibilities that can occur. And this is how the algorithm proceeds. Okay, so here is an example of using the watershed algorithm. So here is the original image and here is the gradient image. Okay, and one can imagine that, you know, if you have this image, a segmentation, what should a segmentation do? It should separate out these blobs. Okay, these blobs you will probably want separated out from the background. That is what a successful segmentation should do. Well, so you look at the gradient image, and to the gradient image, if the watershed now, so in the gradient image, you can imagine that these will be the regions of minima. Okay, so this will be the background region of minima, and for the connected components here, these will be the regions of minima, right? So you can imagine that if you start flooding water through those minimum or those minima, Then as the water, so in the topographical image, as the water rises, it is going to, these are at a higher level of intensity, right? So these are at some height in the topography. So as you fill water, you can imagine that, to avoid flooding between these two regions or these two regions, okay, a dam is built in this way. Okay, so the watershed algorithm will give rise to these watershed lines. Okay, and these watershed lines, if these superimposed on the earlier image, then this is the kind of segmentation that we are getting. So it's successfully segmenting out or separating out the blobs in this image. Okay, so this is how the watershed algorithm works. There is one more thing called markers. So if you, for example, if you use this in MATLAB or somewhere, then it will ask you to mark a region of background and mark a region of foreground in order to do the work the algorithm. So if there's a MATLAB app which does this. So what does that marker mean? So what happens is, generally, if the watershed algorithm is applied as it is to the given image, then the noise in the image, or sometimes there are some spurious extra details, all that will corrupt this gradient image too much. Okay, so if there is noise here, it will all show up in the gradient image. Okay, and those will give rise to too many minima. Okay, which should not be there. Okay, so to avoid that, first of all, one must apply smoothing. Okay, so what smoothing will do is, it will get rid of that noise and those finer details that you don't really need to be segmented out. Okay, so first smoothing is applied, and then, so here, yeah, here there's an example of over segmentation. Okay, so one would want these blobs to be separated out, but there is also some, lighter regions here which you don't want separated out possibly. Okay, but you can see that there's just too many watershed lines here. Okay, this is not going to give you any meaningful segmentation or extraction of these blobs. Okay. Mm. So what is done is, you use some extra information about the image to sort of guide the algorithm to the beginning minima. Okay, so what should be the minima at which the algorithm should begin? Okay, so that is called as a marker. I'm not going into too much detail of this thing. Okay, but that marker can be, I mean, in this app that I was talking about, one does it manually, but you don't have to do it manually. It can also be automated to say that you take the minima to be points that satisfy a certain condition. Okay, and that condition can be based on any feature of the image, based on intensity, of course, but it can also be based on some maybe statistical information or color information. Okay, things like that. So you in the beginning, you provide this extra information about where to look for the minima or which minima should be chosen, rather than let the algorithm choose the minima on its own, in which case it is likely to choose many of those noise or irrelevant detail points. Okay, so that is called as markers. Okay, so the watershed algorithm actually allows the use of this extra knowledge to be incorporated in the algorithm, so that you get a reasonable segmentation. Okay, so I think there is an example of it, of a successful segmentation like that. Yeah, so this image was over segmented in this way, but with the use of markers, where it has been suggested that you use only certain regions as the starting minima, then the segmentation looks like this. Okay, and after watershed algorithm is applied, it will look like this. Sorry, what I should say is, this is the first watershed. Yeah, so this is another thing. The watershed algorithm can be applied in parts in this way. So first, the watershed has been applied to this after doing smoothing and providing markers. Okay, so that is this. Then what can be done is, now you want to separate out or segment out these regions from the background. Okay, so you can apply. So now you look at each of these pieces. Okay, and to each piece you can apply watershed separately, which means suppose you are looking at this region. Okay, so you decide to look at this region. Now apply watershed, which means you will allow flooding from this point and let it rise along the height of this. Okay. Soon as it starts flooding out, you build a dam. Okay. So that will give rise to a much smaller region here. Okay. So because inside this region, you are again applying watershed. Okay. So now you had an earlier set of minima, but now inside this you are not telling it what minima. You can just let the algorithm work on its own. That will provide another set of watershed lines and will segment out this region in this way. Okay. So in this way, the first step, doing watershed with markers, can give you something like this. And in the second step, applying watershed to each of these regions separately can separate out the blobs even better. Okay, so now this image has been segmented out in this way, which is probably sort of the thing that one might be looking for when one looks for segmentation of an image like this. Okay, all right, so that is the watershed algorithm. Again, the implementation of watershed algorithm, there are many implementations, and you know the point in using all those implementations is to understand first what the algorithm is doing. Okay, so I will stop recording this lecture here because I'm done with segmentation algorithm. uh, and what I want to do next is talk about morphology. So I'll record that as a separate lecture. Okay. If you have any questions, you can ask me.